Hi there, welcome to this Elkchemist chemistry video looking at covalent bonding. In this video we're going to look at what covalent bonding is, trying to explain it in terms of electrostatic force of attraction, and I'm going to be drawing lots and lots of dot and cross diagrams. So if asked to define what a covalent bond is, you should say it's a shared pair of electrons between two non-metal atoms. That would represent one covalent bond. A double covalent bond would be two shared pairs of electrons between two non-metal atoms, whilst a covalent triple bond would be three shared pairs of electrons between two non-metal atoms. That definition, however, does not explain how covalent bonding actually works in terms of bonding. Now, bonding fundamentally can be seen as electrostatic force of attraction between particular particles. So the question should really be, what particles are present in covalent bonds that are electrostatically attracting together? Let's go through that now. First of all, let's think about what we've got. We've got two non-metal atoms. At the center of those two non-metal atoms will be two positively charged nuclei full of protons. And we know the definition of covalent bonding is a shared pair of electrons between the two atoms. So there must be in the center a shared pair of electrons, which are both negatively charged electrons. So what's going to attract towards what? Well, it stands to reason that the positive nuclei are going to attract towards those negative electrons in both directions. So this left-hand nucleus is being drawn in this way, and simultaneously this right-hand nucleus is being drawn in this direction. So what do we have going on? Well, we can define this very simply. What we have is a strong electrostatic force of attraction between the two positively charged nuclei and the shared pair of negatively charged electrons located between them. And it's pulling in towards the center from left and right hand side. Now, just before I take you through how to construct dot and cross diagrams, I'll point you this nice table to help you decide how many covalent bonds different elements can form. Let's start off with hydrogen. So hydrogen only has one outer shell or valence electron available. Therefore, it can only form one pair of electrons by pairing and sharing with another atom. So therefore, it can only form one covalent bond. Group 4 elements, like carbon and silicon, for example, have four outer shell or valence electrons, and you can see that none of them have yet created pairs within the valence shell itself. Therefore, it can form up to four covalent bonds. It has four opportunities to share electrons with other atoms to form covalent bonds. That means it's possible for carbon and other group 4 elements to form double or even triple bonds. Group 5 elements, things like nitrogen and phosphorus, have 5 electrons in their valence or outermost shell. 1, 2, 3, 4, and 5. That's one pair and 3 singles. So that has 3 opportunities to form covalent bonds with other elements by sharing electrons. It can form 3 covalent bonds, and double and triple bonds are possible. Group 6 elements, things like sulfur, have 6 electrons in their outermost or valence shell. That's 1, 2, 3, 4, 5, 6. That leaves 2 positions that are unpaired that are available to form covalent bonds, to share electrons with other atoms to get their pairings. So it can form 2 covalent bonds maximum. Double bonds are possible. Group 7 elements like chlorine, fluorine, bromine, they have 7 electrons in their outer shell. 1, 2, 3, 4, 5, 6, 7. That means there's only one unpaired electron available to form covalent bonds. So group 7 elements can only form a maximum number of covalent bonds of 1. So we can see the group number helps us decide how many covalent bonds it's possible to form. Group 7 can form 1, group 6 can form 2, group 5 can form 3, group 4 it's possible to form up to 4, and hydrogen can only form one covalent bond based on the distributed electrons in their valence or outermost shells. Alright folks, let's go through some dot and cross diagrams. I'm going to try and make this as easy as possible. I'm going to try and give you some hints and tips so you get really good at constructing these without making mistakes. So we're going to try and draw a really nice simple example, which is hydrogen H2 first. So what I did is I drew out 2 atoms of hydrogen, one with a dot and one with a cross, 1 electron in each outer shell, so there's only 1 dot and 1 cross present. And then in your mind's eye, you want to overlap these 2 shell diagrams to create a shared pair of electrons. So let's see how that works. So left and right hand side, I'm going to bring them together to overlap my diagrams. And now we can see we have 1 shared pair of electrons in the center of my 2 hydrogen atoms. That would be our single covalent bond. This would be H line H, if we were drawing a line diagram for this, and that would be a successful dot and cross diagram for the molecule H2 or hydrogen. Let's now look at a chlorine molecule. So next we're going to try and draw the diatomic molecule Cl2 or chlorine. So I've drawn two chlorine atoms. They're both group 7 elements with 7 electrons in the outer shell, one with crosses, one with dots to differentiate. Now, a really neat trick you can do here, guys, to make sure you get the right number of available bonding pair spaces is if I draw around singly before I pair up. So for this chlorine here, 1, 2, 3, 4, 5, 6, 7, I instantly see there's one unpaired electron and therefore one opportunity for forming a covalent bond if I overlap with another atom. The same with the other chlorine, I'll see it only has one. So therefore, chlorine atoms, group 7 elements, can only form one covalent bond. So then, in my mind's eye, I overlap the two diagrams to create a sharing area in the center. And I can see there's one pair of electrons being shared in the center. That's one covalent bond. So if I drew this as a line diagram, it'd be Cl, line Cl, a chlorine diatomic molecule. Okay, let's now look at hydrogen chloride next. Now let's try hydrogen chloride. So I've drawn one hydrogen atom, single electron in the outer shell, chlorine atom, 7 electrons in the outer shell. Okay, and then we're going to overlap them and see how many bonds it forms. We have one shared pair of electrons in the sharing area. That's therefore one covalent bond. So it'd be H line Cl, and this would be the dot and cross diagram for hydrogen chloride. Right, let's now have a go at something a bit more tricky, like water. Water is H2O. That's 2 hydrogen atoms to every 1 oxygen. How would I draw a dot and cross diagram for that? Well, I've again followed my own rules. I've drawn an oxygen atom. I've gone round in singles before I pair up my electrons. That's 1, 2, 3, 4, 5, 6. Instantly seeing I have 2 unpaired electrons, 2 availabilities to form covalent bonds, shared pairs of electrons with other atoms. I've drawn 2 hydrogen atoms, each with 1 electron in its outermost shell. And again, I'm mentally going to move these into place to create those overlaps and see how many covalent bonds we'd expect to see in a water molecule. So I'm going to bring one hydrogen to create one pair here, bring the second hydrogen over and create an overlap there. And instantly I can see that in my water molecule, I have a covalent bond between the oxygen and hydrogen here. I have a covalent bond between the oxygen and hydrogen here, and that's my completed molecule. I know the oxygen is correct now because it has its maximum capacity of electrons. Now I include the shared bonds as well, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen has a complete outer shell and has successfully bonded covalently to the 2 hydrogen atoms to form a water molecule. So this is our water molecule. Let's now consider the dot and cross diagram for oxygen. Oxygen is O2, a diatomic molecule. So I've drawn out 2 oxygen atoms, one with dots, one with crosses. Again, I've gone around singly before pairing up, so that's 1, 2, 3, 4, 5, 6 for each of the oxygens. And straight away I can see that each oxygen, both oxygens, have 2 electrons that haven't yet been paired. So I've got 2 opportunities to form covalent bonds with the adjacent oxygen atom. So if I then bring those 2 oxygen atoms together and overlap those 2 areas to create my pairs, I have 2 shared pairs of electrons in this sharing Venn diagram overlap area. In other words, when one oxygen atom bonds covalently to another, we get a carbon-carbon double bond. 2 shared pairs of electrons between the 2 oxygen atoms. So it'd be O, double line O, in a line diagram to represent that oxygen-oxygen double bond. And I can prove that I've got this right because each oxygen should have 8 electrons now in its outermost shell once the sharing has occurred. So this one has 1, 2, 3, 4, 5, 6, 7, 8 in its sphere of influence. And this oxygen also has 1, 2, 3, 4, 5, 6, 7, 8 in its shell. So they both have 8 electrons in the outermost shell. If we go round their shells, therefore this is a successful and stable oxygen molecule. Let's now think about the molecule nitrogen, that's N2. Now I've only drawn one nitrogen initially because I want to talk about how many electrons it has in the outer shell and how many opportunities to bond there are before we bring in the other nitrogen. So here's one nitrogen atom, it's in group 5 with 5 electrons in the outer shell, going around singly first, 1, 2, 3, 4, and then pairing up once. So I can see there's 1, 2, 3 unpaired electrons, i.e. 3 opportunities to form covalent bonds. So if I brought another nitrogen in, it would also have 3 opportunities to form covalent bonds. So what I've drawn is a slight deviation in terms of where I've put those electrons to make it easier to show that overlap. I've got one nitrogen with its 5 electrons. These are still my 3 unpaired, just brought to one side for ease of use. And here's my other nitrogen with its 5 electrons 2 paired and 3 unpaired. They're still quite close, but I've put them on one side because it means I can then overlap them easily in the overlapping area to show they're in there. If the 3 unpaired electrons from one nitrogen overlap with the 3 unpaired electrons on the other nitrogen, when we bring them together, we get this in our overlapping area. That is 3 pairs of electrons in the overlap. That is 3 covalent bonds. 1, 2, 3. So if I drew a nitrogen molecule with a line diagram, it'd be N, 3 lines N, a nitrogen triply bonded molecule. So that's quite an advanced dot and cross diagram, but again, still following our simple rules. Draw out the atoms, see how many unpaired electrons there are, and bring those unpaired electrons together to create covalent bonds, depending on what it's bonding to as to how many covalent bonds it can form to that element. If it's group 7, for example, it'll form 1. If it's group 6, it can form up to 2. If it's 2 group 5 elements, well, they can form up to 3 covalent bonds. If it's 2 of them, that'll be with each other, like in nitrogen. Let's finish with carbon-based molecules, because carbon is by far the most flexible of the elements because it's small, it's got 4 valence shell electrons, it can do all kinds of different bonding. We're going to look at methane initially. That's CH4, 1 central carbon, covalently bonded to 4 hydrogen surroundings. So we've got our carbon with 4 outer shell electrons shown with dots, 4 hydrogens drawn with their single cross to show their 1 outer shell electron. Going to mentally move them into position to create overlaps. So move 1 here, move 1 here, move 1 to the top and 1 into the side, like so. And look what we've made. We've made this beautiful molecule. We've got 4 single covalent bonds, 4 overlapping areas, 1 between each hydrogen and the carbon. The carbon has formed 4 bonds, 1 to each of the hydrogens. So if I drew this with a line diagram, it'd be a central carbon with lines up and out to each of the hydrogens to make a cross formation, and that would be our molecule. Okay guys, we're going to finish up with a challenge. So what I've drawn here is a line diagram representing a molecule known as an alkyne. That's a triply bonded carbon-carbon molecule. This one is the molecule known as ethyne. It's got 2 carbons. What I'd like you to try and do is draw the dot and cross diagram for this particular line diagram representation. So we've got a carbon-carbon triple bond in the center, and then also a single covalent bond to the hydrogens on either side. So think about how you turn this from a line diagram into a dot and cross diagram. Think about what we saw for the nitrogen triple bond diagram. And in 10 seconds, the answer will be revealed. So what I suggest is you pause the video and then play on again, and after 10 seconds, the answer will be revealed in front of you, and it will hopefully match what you've drawn. Best of luck, guys. I'll see you in 10 seconds. And here is my dot and cross diagram representing that line diagram. We've got our 2 carbon atoms overlapping 3 electrons each to create 3 pairs of electrons, i.e. a carbon-carbon triple bond. That's 1 covalent bond, 2 covalent bonds, 3 covalent bonds, and then single covalent bonds between the carbons and the hydrogens on the outside. So that's 1 covalent bond here for that shared pair, and 1 covalent bond for that shared pair there between the hydrogen and the central carbon. Now, making sure these carbons have worked, each one should have 8 electrons maximum in its outermost shell. So that's 1, 2, 3, 4, 5, 6, 7, 8 for this carbon here. And around this shell here, we've got 1, 2, 3, 4, 5, 6, 7, 8. So both these carbons have their complete complement of 8. Each hydrogen has a maximum capacity of 2 because it's only in period 1. So that's 1, 2, and 1, 2. So everything has reached a full outer shell, and this is a stable, triply bonded carbon-carbon molecule. And that will be our last example for the day. Well done, guys. Excellent work. I hope you found this video really useful in how to construct covalent dot and cross diagrams. I really like using these laminate overlays to make it easy to build those pictures. And if you found this video useful, please do think about giving it a like. You could subscribe to the channel. You could ring the bell. Keep notified of the latest content. I put out videos on a weekly basis. You could also share this video and other videos on the channel with friends studying chemistry to help them out as well. That'd be awesome, guys. And as always, it's great talking to you, and I look forward to talking to you in the next Elkchemist chemistry video. Take care. Bye now.